All right, gang. Hello, hello, hello. How are you, my friends? It is time for us to do just a little bit of math again. So, we talked already about how calculus is based off this idea of a limit. And using this idea of a limit, we can come up with instantaneous rate of change, which is a derivative, or we can determine the area or displacement under a curve, which is indefinite integral. Well, we're going to just take this first chapter and just spend some time talking about limit. What a limit is. If you think about the idea of a limit basically means you can't go past it. In math, a limit is basically something where you get really, really close to something, but you don't actually get there. So you get really close, but you don't actually get there. So what we are going to say is that a limit exists when a graph approaches the same point or value from both the left, and later on we'll call that the negative side, and the right, and we'll call that the positive side. So we have this idea that we can figure out when a limit exists. And if you watch the movie Mean Girls, you see her shouting out, "The limit doesn't exist." Well, that's because she's taking a calculus test. But it's the idea that a graph approaches the same thing from the left side and the right side. For instance, here's what I mean by that. Let me write for us a little limit phrase. So this limit phrase I'm going to say is the limit. I'm going to have this x arrow 0 down here, f of x. I don't want to do 0. I want to do 1, actually. Let's make that 1. So this phrase right here, this is a mathematical phrase. And what it says is that the limit of f of x, the limit of the function, when x approaches 1 is, and we're going to say what it actually is. So we're getting really close to something. It approaches, it gets close to. So imagine that I got like a little person or something. So for a little person here walking along here. And as I'm walking down my slope, I'm coming from the left side. And as I'm going to the left side, what value am I coming to when x is 1? Well, if we look here, this is a solid dot. That means this point is at the point 1, 0. So it looks like as I'm coming down along the left side, I'm coming to the point when x is 1, I'm getting to the y value equal to 0. It's the same thing. If I were to come from this side down, I'm also getting that same point. So in other words, what a limit is, it's really nothing more than just pretty much the y value. So as I'm approaching 1 from the left side, I go to 0. As I'm approaching 1 from the right side, I'm also going to 0. That means that the limit is equal to 0. So if we go back to our little phrase here, so then we'd say the limit of f of x when x approaches 1 is 0. So as it's coming from both the left side and the right side, they both approach the same value. Now notice that we don't always have to have a solid dot. For instance, what if I were to do something like this? The limit as x approaches 2 for f of x. Say where I were to do something like that. Well, now my value if I were to come from the left side, I'm going to this hole, this open dot. And that hole is at the point 2, 1. If I'm coming from the right side, I'm going to that same distance. Now, here's the big thing about limits. Limits are not function values. In other words, if I were to ask you what f of 2 is, you'd say f of 2 is undefined. It's a hole. There is no value that it equals. So you'd write f of 2 is undefined. But that's not what a limit is. A limit is very similar to that. You got to remember, a limit, and the really important word we have to think about is the word approach. It approaches. It gets really close to, but it doesn't actually get there. So if I'm getting really close to x equals 2, it looks like the graph is going to 1. Even though f of 2 is not equal to 1, so even though f of 2 doesn't equal 1, matter of fact, it doesn't equal anything. But the limit says, okay, that's fine, but we don't care what it equals, we just care what it gets really, really close to. And if you get really, really close to it, we'd say that is the value of 1. So the function value, it's undefined when x equals 2. However, the limit exists when x equals 2 because it gets really close to, and it looks like it's going to 1. It just never gets there. By the way, that's essentially this thing back in pre-calculus and algebra 2, or pre-calculus and integrated 3. We called that a hole. That's what a hole is. A hole is an x value where the limit exists, but the function value is undefined. Later on, we'll call that something called a removable point of discontinuity. And again, you don't need to worry about that idea for a while. But if we're going to talk about it, might as well talk about it. So this idea here is that a hole, we get really close to it, so the function value is undefined, but the limit actually exists. That's a hole. The limit exists, function is undefined. So there actually was a real thing going on there back in pre-calculus. Well, let's try the next one. What if I ask you to tell me the limit value of f of x as x approaches 3? What would you tell me? Well, let's take a look at this. From the left side, from the negative side, the graph is going to go to the point 3, 1. So from the left side, it goes to the point 3, 1. But from the right side, let's see where that goes to. That's not what I want. There we are. From the, you can almost see it, can't you? There you go. From the right side, if I'm coming up here, notice the graph is going to a different value. From the right side, the point is going to that'd be the point 3, 2. Notice, in this case, they go to different points. They don't go to the same point. Where this one goes to 2, this one goes to 1. And we said in order for the limit to exist, it has to go to the same point. So this limit does not exist. So we would write then that this limit at this function value, we'd say, well, the limit as x approaches 3 of f of x, it does not exist. We want to stay away from the phrase D and E. We don't like using abbreviations in calculus. So we'll literally write out does not exist. This is a limit that doesn't exist. When a limit doesn't exist, we say that that is a non-removable point of discontinuity. Let's write that in there. This is a non-removable point of discontinuity. That's what this is. When the limit doesn't exist, it's a non-removable point of discontinuity. What about if we do one more? What if we say, hey, let's figure out what this limit is when it approaches 4? So when it approaches 4, what happens? If we go from the left side, my graph is going to go down to, if you notice here, it's going down to negative infinity. If I come from the right-hand side, the graph is going to positive infinity. First of all, there is no limit. A limit means it's confined. Well, if it's going to infinity, that means it's unbounded. It's not confined. You can't limit it. So even if it goes to infinity, that limit doesn't exist. Plus, both the left side and the right side, they go to different types of infinity. So we'd say, again, when we're here at f of x, we'd say that this also is a limit that does not exist. And again, if it does not exist, that means it's a non-removable point of I did not spell discontinuity right there, did I, friends? Oh, well. Continuity. There we are. So we have, when a limit exists, that can be it here. Let's pick a different color. There we are. The limit exists when I'm dealing with a solid dot. The limit also exists at an open dot. Because the graph comes to the same point from the left and the right side. Notice though, only at the point 1, 0 is the function defined. It's undefined at this point because it's an open dot. At these two, as x approaches 2, again, we have the limit equal to 1. The limit, as x approaches 3 of f of x, it approached 2 different values. And when it approached 2 different values, when it approached 2 different values, we'd say that the graph does not exist. And then on this one, when it approached the asymptote, again, it was unbounded. So even though it approached 2 different values, it still did not exist. So we're going to look at one other different type of case of, that's what I need over there. I don't want that. Let's get off that though. That's going to cause me some issues later. There we are. There's one other type of case where the limit doesn't exist. And that other type of case when the limit doesn't exist is when we say that a graph oscillates. So far, a graph doesn't exist or a limit doesn't exist, sorry, when 1, it approaches 2 different y values. 2, if it's an asymptote. And then the other one is if it approaches or if it oscillates. And this one is not going to matter to us in Calc AB. We're not going to be dealing with it if it oscillates at a given x value. And here's what I mean by oscillates, for those that don't know what that is. Let's take the function, let's do this one, y equals sine of 1 over x. If you have a graphing calculator, you can plug that in to your calculator to see what happens. If you don't have a graphing calculator, I'm going to give you a real ugly, bad sketch of what's going to happen here. It's going to go up, and it's going to come down, and then it's going to go up and down, and then it gets really close here where it boggles down here a little bit, and then it starts to get away. But what happens here is this point where it boggles down right here, it's bouncing so many times that you can't tell if it's going up or going down or what value it is. That's what it means by oscillate. So we're not going to be dealing with that one in general. We're going to be dealing with these ones. When it approaches two different y values, that's this one. We're going to be dealing with it. We're going to be dealing with it approaches infinity. That's this one. And then if it's oscillating, again, the one that we're not really going to be dealing much with, that's this one right here. So that's oscillating. So that's when our limit doesn't exist. Okay. So we're just going to end here for one little itty bitty second. I'm going to give you guys a few to try. So what I'd like for you guys to do is we're going to be doing this last one down here. It's going to be based off this graph. I'd like you to tell me what is the limit, and this will be the graph of, let's make this one g of x, since we used f of x for the last one. I want to call them the same, so we'll call that g of x down there. What's the limit as x approaches -2 for g of x? I'd like to know what the limit as x approaches -1. I'd like to know what it is when x equals 1, or when x is 1 as well, positive 1. And let's try when x is 2. And last and certainly least, let's try when x is 4. So here's what I want you to do. I want you to go ahead and pause the video. See if you can evaluate these limits at these values. -2, -1, 1, 2, and 4. Go for it. All right, here we go. So at -2, I'm coming up here. I'm approaching positive infinity from the left, and from the right side, I'm approaching negative infinity. And again, because it is unbounded, it approaches infinity. That tells me that my graph here, the limit here, does not exist. Now, when x approaches -1, let's try that one. I'll pick a different color. How about purple? When x approaches -1, it's from the left side, I'm going to pop to -1. From the right side, notice I'm going to the same value. It's a closed dot, so it's defined at -1, but it's also the limit approaches that value. So I'd say then at this point, when x approaches -1, g of x is equal to -1. Notice I didn't put an equal sign here because if it doesn't exist, it can't equal anything. But it does equal a number here, so that's why I put it. Our next one, when x is +1, well, from the left side, I'm going to -2. From the right side, I'm going to +2. So therefore, the limit is -2. Here's a hard one for you. Where does the graph approach at 2? Now notice, this is my function value here, but the graph itself actually approaches the open dot. Since it approaches the open dot, that's what the limit equals. The function value, f of 2, may be equal to -1. But the limit itself, since it approaches here at the open dot, the limit itself equals a +1. I don't know why I put f there. G of 2 equals -1, but the graph itself approaches +1. And let's try one more here. At 4, from the left side, it approaches -1. From the right side, it approaches +2. Since I didn't go to the same value, I say that this graph right here does not exist. What x values is g of x? Does g of x have a removable point of discontinuity? And what x values does g of x have a non-removable point of discontinuity? So again, let's think about what this is. Removable point of discontinuity. This is when the limit exists. But the function is undefined. It has to meet these two scenarios. So the limit has to exist and the function has to be undefined. If it only meets one of them, not necessarily a point of discontinuity. It has to be both. So let's see here. When does this happen? Limit exists, function is undefined. That would be right here at when x is 1. Non-removable points of discontinuity. A non-removable point of discontinuity, that's when the limit does not exist. So that would be when our limit does not exist. Or when the limit exists, but the function is defined. So why don't you guys take a second there and see what values are non-removable points of discontinuity. Technically, this isn't something we're going to actually get to for about another 2 or 3 sections, but I think it's okay for us to kind of look at this from a visual idea. So that way when we kind of deal with the algebraic part of it, we'll understand. So when does the limit not exist? Well, that was when x is 4 and x is -2. Because x equals -2 was unbounded, it went to infinity. When x was 4, it approached 2 different points. But we did have one where the limit existed, but the function was defined. That's at x equals 2. We can't, that would also be considered a non-removable point of discontinuity. All right, friends, so that's a graphical look at what a limit is. A limit is when the graph gets really close to, or it's when the graph is approaching something from both the left and the right side, and it has to approach the same value. So good luck with your homework, and we will talk about this shortly.